Hi everyone, welcome to this tutorial on the ionic basis of the action potential. What we're going to talk about today relates once again to one of our core concepts in the field of neuroscience, and that is that neuroscience communicate using both electrical and chemical signals. So today we're going to talk about one of the most important mechanisms within the nervous system for communicating with electrical signals. We have some learning objectives for you today. I want you to be able to revisit the Goldman and even the Nernst equations and use those equations to gain an even deeper intuition about the membrane potential of neurons, to actually predict that value given knowledge of the concentration gradients of ions and their relative permeabilities across the neuronal plasma membrane. I want you to be able to describe the ionic basis of the action potential in terms of both the voltage and time-dependent changes in ionic permeabilities that occur across the neuronal plasma membrane. I want you to be able to describe the driving force for current flow across the plasma membrane. Driving force will be an important concept that will help you understand the movement of ions through the ion channels that give rise to the action potential, but also through other kinds of ion channels that are gated not by voltage, but by neurotransmitters. So that discussion is coming up in a few tutorials. Now, as you work through these considerations, I want you to relate with careful precision the time course of the changes in sodium and potassium conductance back to changes in the membrane potential during the course of the action potential. And lastly, we'll talk a little bit about what's called the refractory period for the generation of the action potential. So I would want you to be able to characterize and discuss that concept. Okay, well, let's begin by reviewing some of our foundational concepts that we introduced last time. And that is that changes in membrane permeability underlie the neuronal action potential. And in order to understand these changes in membrane permeability, let's consider some of the principles that are laid out in Figure 2.7. Now, recall that during the resting state, there is a little bit of potassium conductance. That is, a little bit of potassium leaks out of the neuron. So the permeability of the neuron at rest for potassium is some small value that's greater than 0. However, the permeability of that resting membrane for sodium is just about nil. So even though the potassium permeability is small, it's still very much greater than the permeability for sodium. So what this means is that in the resting state, the membrane potential is very close to the theoretical limit predicted by the Nernst equilibrium potential for potassium. Now, if we imagine some mechanism that allows for a dramatic increase in the permeability of the membrane for sodium, we may find ourselves in a situation where the permeability for sodium is so much greater than the permeability for potassium that the membrane potential becomes predictable by the Nernst equilibrium potential, or the Nernst equilibrium equation for sodium, such that the membrane potential approaches this theoretical value that we can calculate, the Nernst equilibrium potential for sodium. And this is essentially what happens during the generation of an action potential. The permeability of the membrane goes from being just a little bit leaky for potassium to now being explosively permeable for sodium. And that will explain the rising phase of the action potential. The falling phase, what we find next, is a bit more complicated, but essentially what we can say is that the permeability for sodium returns back towards 0, and meanwhile the membrane restores its resting state where the permeability for potassium is considerably greater than the negligible or the nil permeability for sodium. Okay, now in order to review all of this in yet a different mode of learning, I would encourage you to consider our formal expression for these changes provided by the Goldman equation. And again, I would remind you that the Goldman equation allows us to calculate an equilibrium potential when there may be multiple ions that can permeate through the membrane. So this equation includes a permeability term for each ion that we might be interested in, and it also includes the concentration gradient, which allows us to consider the Goldman equation as an extension of the Nernst equation for permeant ions. Now, maybe this more formal approach is less useful to you. That's okay. If that might be you, then I would encourage you to review these basic concepts of electrochemical equilibrium using the animation provided on the website that supports our textbook. So you can click on the link in your tutorial notes or navigate to that website following the link on our website and select animation 2.2 on electrochemical equilibrium. And that will put you in a great shape to understand the concepts that we need to consider to explain the ionic basis of the action potential. Well, finally, before we get there, I'll just remind you that what we talked about last time is that changes in membrane permeability can have predictable consequences for the change in membrane potential. Now, what we're going to try to explain beginning in this tutorial is how is it that changes in membrane potential can impact membrane permeability. Now, much of the work that I'm going to tell you about in this tutorial and the next one that follows is based on the seminal work of two really just amazing figures in the history of neuroscience, Alan Hodgkin and Andrew Huxley. They were both scientists working in England during the time of the Second World War. Actually, just before it was when their interests were being piqued by the possibility of recording bioelectrical signals from nervous tissue. And then World War II intervened. And, well, depending upon who you are, what your family background is, and the circumstances of your family's journey to where you are today, you might consider yourself fortunate that that great war ended as it did. At least those of us in the field of neuroscience are very grateful for the success of the Allied forces, because that allowed Hodgkin and Huxley to return in the mid to late 40s to their work understanding the ionic basis of the action potential. This work was recognized by the Nobel Committee in 1963, when together with Sir John Eccles, an Australian scientist, they were awarded the Nobel Prize in Physiology and Medicine. I would encourage you to read about their biographies, including that of Dr. Eccles, at nobelprize.org, where you can also find their Nobel lectures. Well, what Hodgkin and Huxley did as one means of beginning to explore the ionic basis of the action potential was to construct some circuitry that allowed them to do the kinds of experiments that they wanted to conduct. They recognized that in nature, we often have wonderful animal models that allow us to address the questions that we want to ask. In their case, they chose to examine the giant axon that's present in the body of squid, which were readily accessible to these investigators in their location in the world. Now, in order to study the ionic basis of the action potentials, they wanted to measure ionic currents. But there's a bit of a problem, because with the generation of an action potential, there is a change in membrane permeability that will alter the flux of ionic currents in a way that would make it very difficult to control and to measure those ionic currents. They devised a circuit called the voltage clamp. And this voltage clamp circuit is illustrated here from your textbook. I don't intend to burden you with the details of this, but I do want you to know that for those of you that are interested, you can read more about this circuit there. Essentially what this circuit does is it provides us with an opportunity for measuring ionic current without changing the membrane potential. Hence this term voltage clamp. We can essentially clamp the voltage of an excitable neuronal membrane to any potential that we wish, and thereby measure the movement of ions across that membrane as we do these kinds of experiments. So I mention all this to say that we do want to look at a couple of experimental results derived from studies that Hodgkin and Huxley did as a means of understanding the ionic basis of the action potential. So, let's begin. Now, what we have here in figure 3.1 from your book is a representation of the kind of data that were available to Hodgkin and Huxley. With the voltage clamp method, they were able to set the membrane potential of the squid giant axon to any value that they wished. And here in this experiment, what's being done is a hyperpolarization of the axonal membrane by 65 millivolts. So they're going from a resting value of about 65 millivolts down to about 130, and then they're holding the membrane or clamping it at that potential for some period of time. And they are measuring then the current that can be recorded during this experiment. So what's seen is a sharp transient, which is called a capacitive current. This reflects the way charge is redistributed around the membrane, but otherwise nothing significant is happening. So with hyperpolarization, there are no significant effects on net current that's flowing into or out of the axon. Now, when they passed a depolarizing current step into this neuron, or in other terms, when they clamped this neuron at a marked depolarizing level, that is around 0 millivolts, so they imposed this depolarization step, they saw something quite different and quite remarkable. Following a sharp transient current, what they saw was a transient inward current that was followed by a delayed outward current. Now, just a word about convention here. In these experiments, inward currents are those carried by positively charged ions into the cell, and our convention is to denote that as negative, whereas outward currents are currents carried by positively charged ions that are leaving the cell, and this is denoted in positive terms. Now, there are other more complicated scenarios that we'll eventually discuss involving negatively charged ions, but for now we can keep it simple. So inward current means positively charged ions are entering the cell, and outward current means positively charged ions are exiting the cell. Okay, well, what we want to be able to do is to understand the underlying changes in ionic fluxes that are explaining these two kinds of currents that were recorded, a transient inward current and a delayed outward current. And in order to get there, Hodgkin and Huxley were able to use both some theory and also some empirical investigation of this system. So the theory comes in the form of the Nernst equation. So Hodgkin and Huxley knew about the equilibrium potentials for permeant ions, even though they weren't sure what those ions were at the time that they began their experiment. They knew that in principle one could determine or manipulate a ionic species that you think might be permeating the axonal plasma membrane and use the Nernst equation to calculate the impact of that permeable ion given its known concentration gradients. Well, I'll just remind you then that the Nernst equation is a tool that can be used in studies of this sort, and I'll use that equation to remind you of this concept of equilibrium potential. So remember, at equilibrium potential, there is no net movement of current. So in an experiment like this, we would record a current of 0 at electrochemical equilibrium. So again, this is the point where the concentration gradient for a permeant ion is exactly counterbalanced by the electrical gradient that builds up with the movement of that charged ion. Now, knowing these two facts, it's possible to do experiments then where we can manipulate the membrane potential of an axon or of a neuron and allow for a prediction on the movement of that ion. And as should be intuitively obvious to you, I think, if you choose to clamp the membrane potential at the equilibrium potential for a permeant ion, then that ion is no longer going to contribute to the measured current, because by definition, at equilibrium potential, there's no net movement of the ion. Okay, so these are the kinds of considerations that are brought to bear in the following experiment. So now, what is being described in figure 3.2 from the textbook is the results of producing an experiment now where there are incremental changes in the voltage clamp setting in the depolarizing direction. So we're starting off at rest, somewhere around 65 millivolts, and we are now applying a depolarizing current step from rest to different values of depolarization. first approaching 0 millivolts and then even going beyond 0 millivolts. That is, making the inside of the cell more positive than the outside of the cell. And what we see is that as we begin to depolarize this membrane from rest, there is indeed a transient inward current followed by a delayed outward current. But notice the magnitude of these currents. With small depolarizations, the currents that are measured are relatively small. With larger depolarizations, like around 0 millivolts, the transient inward current increases in size, as does the delayed outward current. But now look at what happens to the transient inward current as we depolarize to plus 26 millivolts. This transient inward current is getting smaller. But look at the effect on the delayed outward current. It continues to grow in magnitude. Now, we approach plus 52 millivolts in the experimental data. And what we find is, obviously, quite a large growth of the delayed outward current. But notice, the transient inward current seems to have gone away completely. We'll come back to that point in just a moment. But now let's move on. If we depolarize the cell even further, again, we continue to see growth of the delayed outward current in a relatively monotonic fashion as we change membrane potential in the depolarizing direction. But now look at the point in time where we earlier recognized a transient inward current. What we see is a small inflection in the rise of this outward current. In fact, what appears to be happening is that the transient inward current is no longer inward, but outward. And this might explain this small shoulder effect that we see in the development of this outward current. Okay. Well, these considerations allow us to make a couple of points. First of all, we see that this transient inward current appears to be nulled out with membrane potential around 50 millivolts. And then when we go beyond 50 millivolts, or in this result, perhaps precisely 52 millivolts, this inward current reverses. It becomes an outward current. The second observation we make here is that the delayed outward current steadily increases with increasing depolarization. Now we can measure these currents at particular points in time and plot their magnitude as a function of membrane potential. And when we do that, we have data that look something like this, which capture again what we've just described. And that is that with depolarization, the transient inward current grows, but we eventually hit a point of reversal. And that delayed inward current becomes an outward current, with the crossing of 0 millivolts being somewhere around 50 millivolts in membrane potential magnitude.